Time crystals are a fascinating concept in physics introduced in 2012 by Nobel laureate Frank Wilczek. They represent a new phase of matter that breaks the traditional laws of thermodynamics in a way that has never been observed before. A time crystal is a system that exhibits time translation symmetry breaking. In simpler terms, a structure that repeats itself in time rather than in space. In contrast, a time crystal repeats at fixed intervals in time. This means that the system state will oscillate back and forth between two or more configurations without using up energy. Normally, when a system is in equilibrium, like a rock sitting still, its properties do not change over time. This is called time translation symmetry, the idea that the laws of physics don't change depending on when you look at them. Symmetry under translations in space means that the laws of physics are the same no matter where you are in space, and leads to the conservation of momentum. Symmetry under translations in time means that the laws of physics are the same at all moments in time, and leads to the conservation of energy. The symmetry of a physical system, observed or intrinsic, remains unchanged under some transformation. Family of particular transformations may be continuous, such as rotation of a circle, or discrete, example Gracia, reflection of a bilaterally symmetric figure, or rotation of a regular polygon. Continuous symmetries can be described by Lie groups, while discrete symmetries are described by finite ones. A time crystal breaks this symmetry because it oscillates between different states over time, without any external energy input. It creates a dynamic perpetual motion at a microscopic scale, which was previously thought to be impossible due to the laws of thermodynamics. Particularly the second law, which suggests that systems naturally tend to a state of high entropy. In other words, a time crystal continually evolves in time, oscillating in a predictable pattern, but doesn't lose energy, defying the usual notion of equilibrium. In thermodynamics, entropy is a measure of the number of possible configurations or states a system can have. A system that resists entropy would be one that maintains order low energy states over time, perhaps through energy input or other mechanisms. The existence of crystals in nature is a manifestation of spontaneous symmetry breaking, which occurs when the lowest energy state of a system is less symmetrical than the equations governing a system. In the crystal ground state, the continuous translational symmetry in space is broken and replaced by the lower discrete symmetry of the periodic crystal. As the laws of physics are symmetrical under continuous translations in time as well as space, the question arose in 2012 as to whether it is possible to break symmetry temporally and thus create a time crystal that is resistant to entropy. So far, most experimental systems work at very low temperatures. In condensed matter physics, a time crystal is a quantum system of particles, whose lowest energy state is one in which the particles are in repetitive motion. The system cannot lose energy to the environment and come to rest, because it is already in its quantum ground state. Ordinary non-time crystals form through spontaneous symmetry breaking related to a spatial symmetry. Such processes can produce materials with interesting properties, such as diamonds, salt crystals, and ferromagnetic metals. By analogy, a time crystal arises through the spontaneous breaking of a time translation symmetry, breaking a temporal symmetry. Unlike a pendulum, a time crystal spontaneously self-organizes into robust periodic motion. Experimentally realized time crystals show discrete time translation symmetry breaking, not the continuous one. They are periodically driven systems, oscillating at a fraction of the frequency of the driving force. Many systems can show behaviors of spontaneous time translation symmetry breaking, but may not be discrete or flocate time crystals. Many systems can show behaviors of spontaneous time translation symmetry breaking, but may not be discrete or flocate time crystals. Convection cells, oscillating chemical reactions, aerodynamic flutter, and subharmonic response to a periodic driving force, such as the Faraday instability, NMR spin echoes, parametric down conversion, and period-doubled nonlinear dynamical systems, Symmetry breaking can be distinguished into two types, explicit and spontaneous. They are characterized by whether the equations of motion fail to be invariant, which means that the type of differential equations used to describe the law is unchanged in transformation, so that no additional or different solutions are obtained. Bouncing on an oscillating atom mirror, ultra-cold atoms are able to spontaneously reorganize their motion and start moving with a period twice longer than the driving period. The system is in crypto-equilibrium. These oscillations generate no entropy, and a time-dependent frame can be found in which the system is indistinguishable from an equilibrium. When measured stroboscopically, the system exhibits long-range order. The oscillations are in phase, synchronized, over arbitrarily long distances and time. The key novelty of a time crystal is a periodic motion of a system of many objects interacting with each other. Stable examples of spontaneous symmetry breaking, as seen in ferromagnetism or the vanishing electrical resistance of a superconductor, often have significant technological value. A fundamental quantum phenomenon called many-body localization allows a system of many interacting quantum objects to demonstrate periodic motion without breaking the second law of thermodynamics. Rigid subharmonic entrainment can occur in a periodically driven, Fluke, unitary many-body quantum system, dubbed Fluke or discrete time crystals. This new phase of matter exhibits collective subharmonic oscillations that depend upon an interplay of a non-equilibrium, driving many-body interactions and a breakdown of ergodicity. The combination of noise and interactions drives a sharp first-order dynamical phase transition between a discrete time translation invariant phase and an activated classical discrete time crystal, in which time translation symmetry is broken out to exponentially long time scales. Phase invariance means that the fields are not physically distinguishable. First, the system should have many locally coupled degrees of freedom, so that a notion of spatial dimension and thermodynamic limit can be defined. Second, the system's subharmonic response should be stable to arbitrary perturbations of both the initial state and the equations of motion, so long as the latter preserve the periodicity. A system that has time translation invariance keeps rhythm forever, meaning it repeats its motion in a perfectly regular cycle. This is a time translation invariant phase. What is activated classical discrete time crystal? When two things are introduced, noise like randomness or external disturbances, and interactions, the forces between the elements, they start to mess with its perfect regular rhythm. These effects don't just cause a small shift or deviation. Instead, they push the system into a dynamical phase transition, where everything changes dramatically. A first-order phase transition is one where a system goes through an abrupt change, like the instant change between liquid water and steam. The system changes from a stable time crystal phase, where time is still regular and neat, into something messier. It means the system no longer repeats its motion at fixed regular intervals. It gets disrupted and now has periods of erratic behavior, where the oscillations become irregular. These irregularities happen over exponentially long time scales, meaning the system doesn't just snap to chaos immediately. It can take a really long time for it to break down, but it does eventually. The system goes from a state where a time translation is perfectly invariant to a state where it's broken over a super long period, leading to unpredictable activated behavior. This new phase of quantum matter relies crucially on many-body localization to prevent the drive-induced heating of the system to infinite temperature. In many-body localization, the interactions between particles are so complex that they effectively lock the system into localized states, so it's unable to move into the chaos of the larger group. The energy is trapped in these localized spots, and instead of spreading out and heating the system up, it stays contained. This prevents the system from going to an infinite temperature. Degrees of freedom refer to the independent variables or states a system can have. like a collection of little switches or particles that can each move in different ways. The interactions are confined to nearby parts. Why does this matter? When many parts are interacting locally, we can define spatial dimension, how the system extends in space, and consider the thermodynamic limit. Subharmonic response, slow oscillation, should not easily break down when the system is disturbed. Whether the system is perturbed by changing the initial conditions or by tweaking the equations of motion, the rules that govern how the system evolves. The system's response should stay intact as long as the changes don't mess with the overall periodicity, the regular cycle of the system. Is quantum mechanics important only insofar as it allows for many-body localization to prevent heating of the system? How to interpret quasi-energies and fluke states of periodically driven system? An example from the quantum optics could help. A two-level atom could be described by the Hamiltonian. Let's focus on the atom at rest in the electromagnetic cavity and its interaction with a single electromagnetic mode of the cavity, which corresponds to the photon energy. The Hamiltonian of the atom and the quantum electromagnetic field system is presented in the rotating wave approximation, where the third term contains a photon annihilation operator. This is a well-known Jaynes-Cummings model, where the energy of the entire system is conserved. The Hamiltonian matrix could be transformed in a block diagonal form, and the eigenstates are easily found, which in the quantum optics language are called rest states of an atom. The two-dimensional blocks of the Hamiltonian matrix, mean and Hilbert space, can be divided into two-dimensional subspaces. This leads to the dressed atom spectrum. For weak interaction between the atom and the field, the spectrum consists of pairs of energy levels, which are well separated by the photon energy. If there is a large number of photons, the spectrum can be considered as locally periodic because it changes little. Thus, the Fluke-Hamiltonian can be defined. Fluke states of the system are time periodic and can be expanded in a Fourier series. The matrix of the Fluke-Hamiltonian is extended by the time degree of freedom, and the corresponding quasi-energy periodic spectrum reproduces the dressed atom spectrum. So, in a regime of a large number of photons, the quasi-energy spectrum of the Fluke formalism, which treats the electromagnetic field as a classical wave, as something it doesn't have quantum fluctuations, matches the dressed atom spectrum obtained in a full quantum theory of the electromagnetic field. If the quantum field is strong, its modification due to the interaction with an atom can be neglected. Quantum fluctuations of the field are not as significant when the field is intense. The interaction between the atom and the quantum field does not significantly affect the field's behavior, and the Fluke approach allows good enough approximation for the eigenstates of the atom field system. Typically, a classical particle with the least amount of energy is at rest. If a classical particle can reduce its energy by simultaneously performing periodic motion, quantum many-body systems should be capable of doing the same. In quantum many-body systems, the quantum states can exhibit long-range order and spontaneously break the continuous translational symmetry of the system's Hamiltonian. The result is the formation of discrete lattice-like structures, just like in classical materials. The Hamiltonian generally describes the total energy of the system. In the case of conventional space crystals, it includes kinetic energy, describing the movement of particles or quasi-particles, and interaction energy. For instance, Coulomb interactions between charged particles, or interactions between spins. The spins may spontaneously align, which corresponds to the formation of the periodic lattice structure. For time crystals, the Hamiltonian is designed to take into account both the system's intrinsic properties and the periodic driving force, and includes periodic driving terms that interact with many-body dynamics. When we look at a classical particle driven by a period t, it's not unexpected for there to be a stable periodic solution of the Hamiltonian equations that evolves with a period of double t, for example. However, in a quantum mechanical description of the same particle, stationary motion with a period of double t isn't possible. This is because the discrete time translation symmetry in quantum mechanics requires that all periodic solutions of the Schrödinger equation evolve with a period t. Similar band structures can be also observed in propagation of electromagnetic waves in media if the refractive index is modulated periodically in time. The latter systems are referred to as photonic time crystals, which are the time-based counterparts of photonic crystals in space. It is assumed that the Hamiltonian of the solid-state systems includes n particles in a space of some volume with periodic boundary conditions. If the many-body system in any eigenstate is shifted by any arbitrary vector, the n-particle probability density doesn't change. The spatial transformation where you move or shift the entire system by some displacement vector. The system is translationally invariant. Eigenstates of the Hamiltonian are characterized by the well-defined momentum and the completely undefined center of mass coordinates. Totally undefined coordinate, even if a space crystal exists, refers to Heisenberg's indeterminacy principle. Time crystals never settle into a typical state of rest. Even though they are in a lowest energy configuration, these fluctuations could be seen as a manifestation of the energy-time uncertainty, where the time crystal's energy isn't completely constant. The inability to perfectly define both the system's energy and the precise time at which the oscillations are happening. If the Hamiltonian is translationally invariant, so should its eigenstates. It doesn't necessarily imply that a crystalline structure cannot form when we begin measuring particle positions, as there may be strong correlations between the particles. Translation symmetry means that a single particle probability density must be constant throughout space. The kinetic energy of the crystal's localized center of mass is very close to the ground state energy, and significantly smaller than the energy of an optical photon. So absorbing a single optical photon gives more than enough energy to localize the crystal. The equations governing a system have a symmetry, but a system prefers to choose a solution where the symmetry is broken, because solutions that preserve the symmetry are unstable. An eigenstate of the Hamiltonian is a quantum state that, when the Hamiltonian acts on it, results in the same state multiplied by a constant. Introducing a field operator forms a complete orthonormal single-particle basis. A particle is annihilated in the wave functions of certain positions. The Fock state basis is defined for a many-body system. The order of the modes in the Fock states must remain consistent across all calculations. The main idea of Fock states is that they describe a definite number of particles. This contrasts with coherent states, where the number of particles is not fixed, and a system exhibits behavior similar to classical waves. A Hongo-Mendel interference phenomenon is a good example. In Fock states, photons are indistinguishable in a way that leads to this phenomena, such as quantum squeezing and entanglement. For fermions, because of the anti-commutation of the operators, a particle must be annihilated or created first in the mode I, and then in the mode J, or vice versa. The modes with J less than I could be occupied or not, and this dictates the action of the operators. Periodic behavior of the two-particle probability density refers to switching from continuous translation symmetry preserving eigenstate to a symmetry-broken state. After the destructive measurement of a single particle position, which means it annihilates a particle, the remaining particles do not have to correspond the constant probability density. The measurement can either be deliberately conducted or occur naturally due to the loss of the particle from the environment. So the measurement of the particle position is responsible for the spontaneous symmetry breaking. Space crystals are condensed matter systems that, as a result of atomic interactions, can form spontaneously repeating structures in space. The self-organization of multiple particles can only be precisely explained using quantum mechanics, and it involves a spontaneous breaking of the continuous spatial translation symmetry of the many-body Hamiltonian into a discrete one. This symmetry breaking can also be seen in systems that are quite different from space crystals. For instance, non-interacting systems, because the particles are indistinguishable. The position of the first particle can be measured with equal probability density at any location. Continuing the calculation of the conditional probability leads to an interference pattern. The periodic distribution of particle density for a single instance of measuring the positions of all particles initially prepared in a Fock state. However, the location of its maximum will change in different repetitions of the same experiment. Before taking measurements, we cannot predict where the interference fringes will appear. In space crystals, the question is whether the likelihood of detecting particles varies periodically within the space configuration at a specific moment in time. That is, at the instant we measure the particles' positions. When transitioning from space crystals to time crystals, the roles of space and time are reversed. In time crystals, the spatial position is fixed, and the question is whether the probability of detecting particles at that fixed location changes periodically over time. Time-independent systems exhibit a symmetry in time translation, meaning that the eigenstates of the Hamiltonian are also eigenstates of the time translation operator and can enter a state of periodic motion even when subjected to the vanishingly small disturbance. Applying a time shift to the system doesn't affect its energy states. When the Hamiltonian of a time-independent n-particle system commutes with the time translation operator, energy eigenstates are stable, the particles are interdependent, and their collective dynamics can lead to collective effects. For instance, in a system of interacting spins, like the Fluke time crystal, the spins can evolve periodically and exhibit oscillations with a longer period than external one.